Okay, so what we're doing here today is we're going to go over what's called the Parallax Lab. And the Parallax Lab is a lab to show you how objects appear to change direction when they in fact haven't changed direction or position. It has to do with the position that the observer has changed. And it has a lot to do with the reference of objects behind it. In other words, if all objects were the same distance, then you wouldn't have parallax effect. The reason parallax actually occurs is because there's objects that are behind the object you're looking at. And when you move your position as if the Earth revolves around the Sun, it changes the position or the angle from which it's viewing that object. So it makes it look like it's in a different position relative to the objects that are behind it. And this is a good lab to sort of demonstrate that. There's a couple things you're going to need. You're going to need a light source, which is going to represent your star. You're going to need some masking tape so that you can pinpoint some specific locations. You're going to need a paper clip, which is just a formality, but it may help keep some things together. You're going to need something to write with. Black and red pencils are optional, but you can use them. You're going to need a couple of rulers and a meter stick. You're going to need some paper, calculator, you need the lamp, and a couple index cards. And what I'll do is I'll read through the procedure and I'll kind of give you a visual of what everything should sort of look like. This way you can use it as a resource, or if you're at home you can sort of participate in the lab. And I'll give you a couple data points, but not too much to give all of the information away, just enough to sort of give you an overview of what to expect in the lab. So the first thing I want you to do is to place the lamp in the middle of the lab station. This is going to represent the orbital plane of the Earth revolving around the Sun and other planets, or the Sun, but other planets are also revolving around the Sun at the same time. And what you want to do is you want to pick one end to start from. So we're going to pick this as our starting end. And what we're going to do is we're going to place the lamp in the middle of the table, roughly about 80 centimeters from one end of the table. And you don't want to move the lamp after you do this. So you want to make sure you're choosing the correct side of your meter stick. One side is metric, the other side is inches, and we're going to be working on the metric side. So we're going to go ahead, we're going to take this meter stick, and we're going to place it right here in the middle of our lab table, and we're going to find the 80 centimeter mark. And you know, it's important here that we choose how we're going to record our data. Are we going from the front of the bulb, the back of the bulb? It doesn't really matter how you do it as long as you're consistent in what you do when you're recording all of your data. So the best way to do this so that we don't damage any bulbs here is to sort of just put this tape right on here. And at the same time then you want to make just a little mark in front so you remember where that 80 centimeter mark is. Okay. The next step is to measure from the front of the box, the end with the hole. So you'll notice there's this box, and this box actually has a hole at one end and it's solid on the other. It's going to act sort of as a telescope, and light is going to pass through it. And when the light passes through it, it's going to create a dot on the inside of the box. That dot is an important piece of information that you're going to use to measure. So measure from the front of the box, the end with the hole, to the rear of the box. This is what we're going to call the focal length. So in your lab, you're going to have a data table. And in that data table, it's going to ask you for the focal length. The focal length is the measure from the front of the box to the rear of the box. So in this case, we're going to use our ruler because it's a little bit easier to measure with. Again, we're going to find the metric side. And when we do that, we find it's roughly about 9.5 centimeters. Now you'll notice that the box sometimes warps in. You might want to make sure that it's nice and square. So about 9.5 centimeters or 95 millimeters. So you record that in your data table. Now when you're doing this, keep in mind that there are certain things that are constants, things that don't change. That might be one of them. Step number 3. Place the box, which is your telescope, on the lab table so that one hole in the box points towards the light source. So here's our box, here's our hole, pointing towards the light source. Line the left side of the box up with the left edge of your lab table. Make sure the box is as close to the edge as possible. In other words, you want to take your box and you want to move it to the left edge. This is your left, the left edge of your table, so that the dot is pointing toward the light source. There's a little diagram in here to show you that as well. Put a small piece of tape on the table below the hole in the box. It's important that it goes below the hole because that is where the light is actually entering. So we're going to go ahead, we're going to put a little piece of tape right below the hole in the box. Try to get it as close as possible. Remember, you want to be as precise as you can. Use a pen to make a mark on the table, make a mark on the tape directly below the hole. This mark represents the position of the telescope when Earth is at one side of its orbit. So what you're essentially doing is you're sort of replicating that Earth is going around in an orbit. So the Sun is over here. The Earth is going around in an orbit. And you're taking this parallax measurement from one end of its orbit to the other end of the orbit. Okay, so this represents one position of Earth's orbit. Using an index card, place the card inside the box so that the light shining through the hole is visible on the index card. So here's your index card. You may have to fold it, and you want to place it inside the box at the rear of the box. And the reason we place it at the rear of the box is that's where the light's going to hit. And we're going to reuse these boxes. So the marks that you're going to make are going to be on the index card. You also want to make sure that your index card is full very nicely so it doesn't open up. Because if it opens up, then you're changing the focal length of the box. Okay, so you want to go ahead, put that in there like that. Maybe you have another lab partner here who will hold that for you. Now you're going to turn the light on. You turn the light on, there's going to be a dot in the rear of that box. With a pen or pencil, mark the paper where you see the dot of light. Label this P1. Position 1. So we're going to go ahead and we're going to mark a little dot there. Move the box to the opposite side of the table, just like it was on the left side. So now you're going to move the box to the opposite side of the table. The dot is going to move because the angle from which you're viewing this star has moved. Put a small piece of tape on the table below the hole in the box. Use a pen to mark on the tape directly below it. This mark represents the position of the telescope when the Earth is on the other side. In other words, 6 months later, the Earth is now revolved all the way around. So you're going to place another piece of tape right there. Repeat step 7, which is to take your pen and mark the inside of that box. Now what you have are two dots, one representing one period in the Earth's orbit, and the other, another period 6 months later. Using a formula in the lab, you're going to measure the distance between that using your ruler, and you're going to use a particular math formula, and you're going to actually calculate how far away that box is from that light source. But in order to know if you did it correctly, you need to actually measure it, which we're going to call our known distance. So keeping the box either in that position or the other position, you're going to take your metric meter stick and you're going to place it in front of the dot, not to the left of the box, to the right of the box, or whatever, in front of the dot. And you're going to remember, we talked about consistency. We're going to measure from the front of that all the way to the front of the light bulb, and we end up here with 76 centimeters. So that means that when I take my measurement from this dot to that dot, and I use my math formula, I should get an answer that is pretty close to the actual distance, which is 76 centimeters. And this is how you're proving whether or not parallax is actually an effective way to measure the distance of objects from Earth. And that's basically the whole gist of the lab, is to sort of validate the whole process of using parallax. The next step is then to move the light bulb. And so you're going to move the light bulb a little bit closer, and then you're going to move the light bulb a little bit further from its original starting position. So that's going to help you validate whether or not an object closer to Earth has a bigger or smaller parallax than objects that are farther away. In other words, if you had two objects that were in the sky and one had a greater parallax shift, could you determine whether or not that object is indeed closer or further from the Earth? I hope this helps. And again, if there's a data table, make sure the data table is filled out. You want to make sure that your units are all the same. You want to make sure if there's any conversions that you have to do, that you do that. If it asks it in millimeters, you want to make sure you convert your centimeters to millimeters. There is graph paper in here. There's also a list of questions that you need to complete. There's also a sketch of the experimental design. In other words, you want to put a drawing to your lab report so that if someone else were to do this and they didn't have this video, they would at least be able to look at the sketch and get a general idea. It's kind of like reading directions and having a picture to go along with the written directions. The other thing you're going to need to add is a conclusion, and there is a rubric that goes along with the lab.